Okay, we're going to be studying quadratic functions. This is what you've been leading up to from the previous chapter. The standard form of the quadratic function is the quadratic equation f of x equals ax squared plus bx plus c. Now the a stands for the number that's in front of the x squared, and in this case down here, what number is in front of this x squared? Yes, a 1, because if there's no number in front of when multiplication is involved, that means there's a 1 there. In this case, the a is a 5, and in this case, the a is a 3. bx. So the number in front of the x is the one that is the b. So in this case, b is 3. In this case, b is 2. And in this case, there is no b, so that means that b is a 0, okay? Because when it's involving, not multiplication, addition and subtraction, if there's nothing there, there's a 0 there. The c is a constant number, or a number that does not have a variable with it. So when you look down here, the constant, or the c, is 2. In this one, the c is a 0, and in this one, the c is a 0. The only one that can't be a 0 is the a. Because if the a is a 0, then it's no longer a quadratic equation because it doesn't have an x squared in it. You've been dealing with graphing lines. Now you're going to be graphing parabolas. A parabola is shaped like this. It has an open side and a closed side. This is the open, this is the closed side. It can face up like this one, or it can face down like this one. When I say facing down, I'm talking about the open side is down, okay? Or facing up, the open side is up. The vertex is located at the lowest point or the highest point on the parabola, okay? On the closed end. When it faces up, the lowest that the vertex can be located is called the minimum. That is the lowest y value. In this case, the lowest y value is -9. So the minimum would be -9. In this case, the maximum value is 7. When a parabola opens down, then it has a maximum. When it opens up, it has a minimum. The vertex in this case is located at 4, 7, and in this case it's located at -3, -9. Now tell me, does this one have a maximum or a minimum? Yes, it has a minimum, and it's located right here, and that would be 1, 2, 3. The minimum is y equals 3, okay? And the vertex would be 1, 2, 3, 4, 5, 6, 1, 2, 3. The vertex is 6, 3. Alright, does this one have a maximum or a minimum? Right, it has a maximum because it's facing downward. And the maximum value is 1, 2, 3, 4, 5. So the maximum value is equal to 5. Excuse me. Alright, now, what is the vertex on this one? The vertex is -1, 2, 3, -1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the vertex is -5, +5. One more. Does this one have a maximum or a minimum? Correct, it has a minimum, and the minimum is located at 1, 2, 3, 4, 5, 6. So the minimum, I'm having a hard time with my marker here, I'm sorry. The minimum is -6, and the vertex is located at 1, 2, -6. The vertex is 2, -6. The axis of symmetry. The axis of symmetry divides the parabola into 2 equal parts, like a reflection in a mirror. This is the axis of symmetry. This one, and this one are all axes of symmetry. if you notice, the side on the left is the same as the side on the right of the axis of symmetry. And each point on this side is the same distance from the corresponding point on this side. If you notice, this one is 1, 2 away from the axis of symmetry, and this one is 1, 2 away from the axis of symmetry. This one is 1 away from the axis of symmetry, and this one is 1 away from the axis of symmetry, because they are mirror reflections of each other. If you fold it on the axis of symmetry, then the two sides will lay on top of each other. Oh, the axis of symmetry also passes through the vertex of the parabola as well. Okay, now we're going to get into graphing a quadratic equation. It doesn't matter what numbers that you choose for the x value, but you're going to choose some numbers for the x value, plug them in, and find out what the y value is. It's always a good idea to try 0, because 0 is the easiest number to try. And then the other ones are just up to you, numbers that are easy for you to use. So let's try 1. Y equals 3. So that would be 3 times 1 squared, and 1 squared is 1, plus 6 times 1 minus 4. So what does that give us? That gives us 3 plus 6 is 9, minus 4 is 5. Whoops, excuse me. Gives us 5. So 1, 5. So we come over here and we go 1, 1, 2, 3, 4, 5, and we put a dot. Okay, then we got 0. If we put 0 in, that makes 3 times 0 is 0, plus 6 times 0 is 0, and we're left with negative 4. So 0, negative 4. So we come over here to plug in 0, 1, 2, 3, 4. 0, negative 4. Now we plug in negative 1. Negative 1 squared is positive 1. 3 times positive 1 plus 6 times negative 1, because that's the thing we're plugging in, minus 4. So that gives us 3 minus 6 is negative 3, minus 4 is negative 7. So we come over here and we plug in negative 7. Negative 1, negative 7. Negative 1, 1, 2, 3, 4, 5, 6, 7. Okay? Now we do negative 2. Negative 2 squared is 4, so 3 times 4 plus 6 times negative 2 minus 4. So that gives us, well, my marker's giving me trouble. I really apologize. 3 times 4 is 12. Minus 12 is 0. Minus 4 is negative 4. So we have negative 4. So negative 2, 1, 2, 1, 2, 3, 4. All right, do you notice something here? This one and this one are on the same y value down here, and this one is in between them. It looks like this is the vertex and this is the axis of symmetry going in between them right here. So one thing you can guess now is that if this one is the same distance from here as this one is from there, then this one probably is the same distance as its corresponding part on the other side. So let's try this. This one is 1, 2 away, so we can go 1, 2 away and put our mark. And just for surety's sake, let's go over here and find out and make sure that we're right. We go 3 times negative 3 squared, which would be 9, plus 6 times negative 3 minus 4. That gives us 3 times 9 is 27, minus 18 gives us 9, minus 4 is 5, which is what we expected it to be. So now we can come over here and draw our our parabola, if I can do this well with the way my marker is doing today. And that's probably one of the most horrible parabolas you'll ever see. Okay, and by the way, down at the bottom it's always curved, not a V. Okay, that's a completely different function. We'll struggle through with this marker the way it is, and let's see how we do. All right, so now we've got y equals negative 2x squared. We'll let x equals 0. So if x is 0, then y is going to be negative 2 times 0 squared is going to be 0. So we got 0, 0. So we come over here and put 0, 0. Then 1. 1 squared is 1 times negative 2 is negative 2. So we got 1, negative 2. Negative 1. Negative 1 squared is 1. Negative 2 times 1 is negative 2. So over here we've got negative 1, negative 2. We see a pattern developing. At 2, 2 squared is 4. Negative 2 times 4 is negative 8. So we come over here and we go to a 2. 1, 2, 3, 4, 5, 6, 7, 8. And we put our dot right there. And then negative 2. Negative 2 squared is 4 times negative 2 is negative 8. And we come over here and we put our dot at negative 2, negative 8. And we draw our parabola. There we go. And if you notice that whenever it does not have anything out here after the ax squared, if it doesn't have bx plus c, then it started at the vertex right here. Okay, it started at the vertex. The domain and range. Any domain is the possible x values of a function. The range are the possible y values. So, what are the possible x values of the parabola that you see to your left here? The x values start about at the vertex here, and the first x value would be 1, 2, 3. The next one would be 4, then 5, 5.2, and the parabola keeps on going. The ones that I'm able to draw with the draw function here on this application tend to go straight down, but it really goes more like out like that all the time. Okay, not quite like that, but anyway, it continues out. So that means that it continues out, getting further and further to the right on the x values, and further to the left on the x values. So that means that all x values are possible for the domain, which means that the domain is all real numbers. Okay, all real numbers. Now the y values start at 1, 2, 3, 4, 5, 6, 7. They start at 7. And this one has a maximum. That means that the maximum it can be is 7, but it can be less than 7, and it can be 7. So that means we write y is less than or equal to 7. So the range is y is less than or equal to 7. What are the possible x values or the domain for this function? Well, it's similar to the other one, so that means that, well, actually, let me tell you this. Whenever you have a parabola facing up or down, the domain will always be all real numbers. Okay? The only other time that it will be different is whenever we end up having a parabola that looks like this, and you're not dealing with that this particular moment, okay? So right now it's always going to be all real numbers. The one that has the different values right now will be the range. The range on this one, it starts at positive 2 and goes down from there. So we want to have y is less than or equal to 2. The domain on this one is once again going to be all real numbers. And the range starts at -1 and goes down. So that means it will be y is less than or equal to -1. Now let's look at this real quick here. If it had been like this and we flipped it, well, I didn't get it, did I? And we flip it, okay, well, what happened? There we go. And we flipped it and we put it right here. Now the possible values for the range would be y is greater than or equal to -1. See, it starts at -1 and goes up. Okay, so that's the difference in the way these are notated, okay? Everything starts with the parent function. Then numbers are added which tell you how to manipulate the graph. The parent function is f of x equals x squared, and it starts at the vertex, the origin right here, faces up, and starts out with 1, 1, 2, 4. The next would be 3, 9, and the corresponding sides on the other side. But it's just the squared values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. And it looks like this. So this is the parent function. Everything begins with the parent function. All right, we've got the parent function here. Now let's see what these would look like compared to it. We've got y equals 2x squared. If I let x equal 0, what will y be? 2 times 0 will be 0. So it starts out at the same place. If I let x equal 1, then 1 squared is 1, times 2 is 2. So at 1, x will be 2. If I let x equal -1, then -1 squared is positive 1, times 2 is 2. So -1, 2. If I let x equal 2, then 2 squared is 4, and 2 times 4 is 8. So we go over here, 1, 2, 3, 4, 5, 6, 7, 8. And the corresponding point on this side will be 8 as well. So when we graph that, then we look sort of like, I hope I can do this okay, we look sort of like this. And you notice the graph is a little skinnier, okay? The graph is a little skinnier. Now when we do -3x squared, if we let x equal 1, then 1 squared is 1, times -3 is -3. 1, 2, 3. Corresponding point on the other side will be right here. If we let x equal 2, then 2 squared is 4, times -3 is -12. Well, -12 is going to be way down here, and the corresponding point will be here on the other side. Now we've got a graph that looks like this. What do you notice about the graphs? Ooh, these parabolas are difficult to draw. All right. The first one, 2x squared, was skinnier or stretched vertically, more stretched vertically than the parent function. The -3x squared was stretched vertically or skinnier than the previous function. So what could you predict about the 4x squared? It would be even skinnier or stretched vertically than the previous two. So it would look sort of like this, okay? Just a rough drawing of it. Would look something like that. So what can you conclude from this kind of information? You can conclude that as the number in front of the x squared, the a, gets bigger, 2, 3, 4, the graph will be stretched vertically more or get skinnier. It doesn't matter if it's negative or positive, it's just the absolute value of the number. So 2, 3, 4, 5, they get skinnier. If they get skinnier whenever we're talking about numbers that are greater than 1, what do you suppose will happen for numbers between 0 and 1? You probably already know this, but let's go ahead and try one. If we let x equal 2, then 2 squared is 4, and half of 4 is 2. So we come over here to 2, 2. Corresponding point on the other side will be right here. Now we've got 4. 4 squared is 16 times 1/2 is 8. So we come over to 4, 8. And the corresponding point on the other side is right here. Let's try to draw a graph of that. Oh! And you notice that it got fatter or more compressed vertically, okay? Compressed means you push down on it and it becomes more, like I say, becomes fatter as a graph. So as the numbers get smaller as fractions, okay, 1/2, 1/3, 1/4, then that means that the graph will get fatter is the easiest way to say it. The technical way to say it is it's compressed, they become more compressed vertically, okay, compressed vertically. So when the absolute value of the number in front of the x squared is greater than 1, the graph is stretched vertically. It looks like this normally, it becomes like this. When the absolute value of the number in front of the x squared is less than 1, between 0 and 1, the graph is compressed vertically. In other words, it becomes fatter. All right, what about this one? What will it look like? It will be a very skinny graph or stretched vertically. This one will be a little bit less skinny or a little bit less stretched vertically. And this one will be compressed vertically or a little bit fatter than the normal parent function. A negative sign in front of the x squared causes the graph of the function to flip over the x-axis. You've seen this as we've graphed a couple of these, that when there was a negative in front of it, it caused the graph to face downward, okay? That's what a negative does. It doesn't affect what the graph looks like, except as far as skinny or fat, all it does is it tells you which direction the graph is facing. A number following the x squared indicates whether the function moved up or down the y-axis. Like this, the number following right here is a positive 1. A positive number indicates the graph moved up the y-axis that many units. So in this case, the parent function is right here. This function moved up 1, okay? In this case, a negative number indicates the graph moved down the y-axis that many units. So we've got the parent function right here. Whoa! Oh, that's so horrible. Just bear with me on that. And then the parent function would be way down here. Moved down 6, I mean not the parent function. The new function would be moved down here 6 places. So, the black one here is x squared plus 4. The parent function would have started here, but this one goes 1, 2, 3, 4 up. Okay? On this one, the parent function would have faced up and started at the origin, but the negative sign caused it to flip. So it flipped downward, and it moved up 2 places because of the positive 2. X squared minus 6. X squared minus 6 is the black one here. it moved down 1, 2, 3, 4, 5, 6 places. Negative x squared causes it to flip, and it moved down 8 places. So tell me what happened to these. This one moved down 5 places. This one got fatter and moved up 7 places. This one flipped, was stretched vertically or got skinny, and it moved up 3 places. This one got fatter or was compressed vertically and moved down 9 places.